So, welcome back again, and we pick up from the last lecture where I explained to you Kirchhoff's laws, the KCL and the KVL. Okay, and today I'll take some of the applications, and one of the applications which is of interest to us is a Wheatstone Bridge. I talked to you about Wheatstone Bridge when we were discussing capacitors, but right now in this DC application we have a Wheatstone Bridge which has got 4 arms: R1, R2, R3, R4 are the resistors. Okay, R4 is a standard resistor and R3 is an unknown resistor, so we have to find out the value of any of these values. This could be a standard and that could be unknown, etc. And this could be a standard and this could be we have between the points B and D there is an instrument which we call a galvanometer. Galvano means current meter. But this instrument has the beauty of staying in the middle, and then if the current is in one direction, it goes like this, and the current is in this direction, then it goes like this. The current is proportional to the deflection. Okay, the more the current, the more the deflection. Now, while we are discussing this Wheatstone Bridge, we take the condition that the potential over here and the potential over here, VB is equal to VT. So there is no potential difference in this R. And what I have shown, the current IG through the galvanometer, which has a resistance RG, okay, because galvanometer is made of wires, and those wires, they carry resistance. Okay, so there cannot be a galvanometer with a zero resistance practically. Of course, a galvanometer can be converted into an ammeter, which is a current measuring device, also in a voltmeter, which is a potential difference measuring device, by doing some interesting variations over there. Normally the ammeters, they have very low resistance. Ideally they have zero resistance, and voltmeters have infinite resistance ideally, but very high resistance. So what happens is, between A and C we have applied a battery, okay, with an EMF E and of course an internal resistance which is equal to approximately equal to 0. R tends to 0, and we take it to be equal to 0. So with this, now what I say is that let this current be I1, and this current is I2, okay, and you can see that this current is I, so this is the incoming current, so I will be equal to I1 plus I2. And here I have the current I4. Sorry, okay, let me make this R4 and let me make this R3, it doesn't matter. Okay, so R3 becomes the unknown and R4 is the standard resistance, whatever, it doesn't matter. Okay. So under the condition of balance, you can see that IG is equal to 0, there VB is equal to VT. No potential difference exists. Then we apply KCL, Kirchhoff's current law, that's junction rule at the junction B. So this is already equal to 0. So this I2 minus I4 is equal to 0. So I can get this relation that I2 is equal to I4. And similarly, at this junction, I1 will be equal to, I1 is the incoming current, I3 is the outgoing current. So if we take incoming current as positive and outgoing current as negative, so we get a relation like this, which gives us, okay, I1 is equal to I3. Okay. Now let us apply Kirchhoff's voltage law, which is the loop law, and we take a loop A, B, D, A. Okay. So if I do so, then I can write R2 into I2 plus 0 plus R1 into minus I1, because we are going like this and the current is coming like this, which has already been shown. Okay. So from here I can write that R2 I2 is equal to R1 I1, or I1 upon I2 is equal to R2 upon R1. Okay. So now similarly, if I apply C, B, D, C, this is anti-clockwise. The first one was clockwise. Doesn't matter which way we go. We can have any choice. Okay, you could take like this also. Same result will be obtained. So you have the freedom. So minus R3I2. Okay. Minus R3I2. Oh, R4I2 minus R4I2 minus R4I2 plus 0 plus, when we come back like this, so I3 into R3, which is I3 is equal to I1, so this is R3. Doesn't matter much. Okay, so this again culminates into R4 I2, R3 R1 I1. Okay. R4 I2. Okay, so I1 upon I2 becomes equal to I1 upon I2 becomes equal to R4 upon R3, no matter, R4 upon R3, R4 upon R3, doesn't matter. Okay, what we get? So R2 upon R1 is equal to R2 upon R1 is equal to R4 upon R3, R4 upon R3. Okay, which gives R2 into R3 is equal to R1 into R4. Okay. R4. So from where I get the relation, if you want to calculate what is the value of R4, then it will be R1 R3, R2 R3, R2 R3 upon R1. Doesn't matter. Okay. You can scribble and you can obtain the result. The main things are two. Okay. Now, look here. I can say this upon this is equal to this upon this. Or this upon this is equal to this upon this. Okay. Adjacent branches. We can also say that R2 into R3. R2 into R3 is equal to R1 into R4, which means the resistor and the resistor in the front, their product is equal to the other resistor and the resistor in the front. So which in Hindi Urdu I can say Amne into Samne is equal to Amne dash into Samne dash. Okay. So this is how we look at the Wheatstone Bridge. So continuing with that, the application of the Wheatstone Bridge. Okay. This is one of the simplest bridges which used to be available to us when we were doing our intermediate classes. Okay. Well, this is the setup. We do the experiment everywhere. These are some thick copper strips on a board, okay, and here are screws by which we can fit resistors R and S. I'll tell you what they are. And then there is a point B, and between B and D where there is jockey, I have a galvanometer, which is a sensitive galvanometer. We slide this jockey such that the current in the galvanometer becomes equal to 0. Ig is equal to 0. This is 1 meter long, 100 centimeters, and this measurement we can do with the help of a meter scale, which is fixed onto the block of the instrument. Okay. You can look for a better diagram. Here it is a key, okay, which we insert while we are doing the experiment. Okay. There is a key, K, I can write here, and this is inserted while we are doing the experiment. Of course, there is a supply which may have some internal resistance, may not have, doesn't matter at all, because once the system is there, then it doesn't matter what is the value of the current which is coming, and of course the same is exiting out of this junction C. Okay. When the current in the galvanometer, and the galvanometer is something like this. It has a key, it has an indicator which is normally in the center, and if the current is in one direction, it goes like this. If the current is in the other direction, it goes like this. What we have to do is we have to get the value of the current, because if this is the balance condition, and if I take it on this side, then maybe the current goes this way, and if I take this balance position on this side, then the current goes the other way. Okay. There are means by which we can make this galvanometer more sensitive by shorting the terminals, which we'll talk about when we are talking about the ammeters and galvanometers, etc. Okay. So in the meter bridge, the wire length is 100 centimeters, okay, and we have a wire between these points A and C, which are 100 centimeters apart, and this is checked in the beginning if it is exactly 100 centimeters or not, and there are screws to fit it and make it this tight, so the jockey can slide over this wire, and we can check from the meter scale as to what is the markations from 0 to 100, and we can find out the value where the even in the case of the sensitive galvanometer, the deflection is 0. Okay, so that way, now I take rho as resistance per centimeter of the wire, and the wire is supposed to be of uniform area cross section, made of the same material, okay, drawn from the same material. Normally it is a nichrome wire, and it doesn't matter if the resistance of the wire changes with weather, whether we do it in the cold days or in hot days, it doesn't matter at all. So when Ig is equal to 0, Vb is equal to Vd, this is the condition, and I have translated this thing in the form of what is known as the familiar Wheatstone bridge. So this is A, B is jockey point, D when the Ig becomes equal to 0. So Rs, and this is L1, so rho into L1 and rho into 100 minus L1. etc. And we can see from the condition of the Wheatstone bridge that this upon this is equal to this upon this. Okay, so I write the equation R upon rho L1, S upon rho 100 minus L1. So rho and rho will cancel out, and I can write the value of R as equal to L1 upon 100 minus L1 multiplied by S. Okay, the value of R therefore depends upon the value of S. It is advised that for the maximum sensitivity to find out the value of R, the value of S should be chosen such that L1 is somewhere in the middle of this scale, near to this one. Anyway, what we can do is we could change the value of S, and the L1 values are also going to change, and for a number of values of S we calculate the value of R, take their average, estimate that average, and that is the resistance of this in terms of the resistance over here and the length at which it has been. There are many other variations of Wheatstone's bridge. For example, Carey-Foster's bridge and many other things which are available. And the bridges, they function not only on a direct current, but there are AC bridges also where we require some kind of detection mechanism by which we say sometimes between the point B and D we have a headphone in which there is a buzzing sound, and we try to minimize that sound in the case of alternating currents and the bridge addressing the alternating systems, where the value of instead of the resistances that we are taking, we can take impedances and calculate the value, obtain the value by practical means. Okay. There are many things which are done. For example, I can reverse the direction of the current and again find the values L, etc. Okay, we can exchange these two positions and again find the value of R. So just to minimize the errors, if any, because errors do crop in, okay, in experiments, and we are asked by our teachers to write precautions and sources of errors. I never subscribe to these terms, precautions and sources of error. Instead, I always say that it should be sources of error, possible sources of error, and the precautions that we have to take. So the sources of error have to precede this precaution part, and we have to take precautions in carrying out. Then there are human errors, there are errors in measurement of L1, etc. They are possible, and therefore we can calculate, tell as to what is the error factor. Okay. So for the day, thank you very much. And the next thing is again almost, that's a beauty, that's called potentiometer, and we are going to talk about potentiometer and what kind of experiments we can do with the potentiometer briefly, and end up by finishing this particular chapter before going to magnetic effect current. Thank you very much.